I'm not sure.
Yes. What? If you want, sure.
Guys. Happy birthday to you. Happy birthday to you. Happy birthday, dear Jacqueline. Happy birthday to you. Oh, come on.
Nah. Meanwhile, she's over there like, I'm the killer.
I forgot how to spell her name.
Oh, the Sophie Davis song? Because they always have
That's what the Q is.
Jacqueline.
Oh, Jacqueline.
Pay attention.
Who's Jacqueline?
I think we should go like a math class in
Bruh.
He asked me who's Jackie was too, so I'm not really looking at
This is crazy.
Oh, C-Q-U-E. Okay, now, birthday gift is applications.
Wow, didn't even get it.
So yesterday we heard the most important information in our entire lives.
And
Now we're actually going to use that information.
In the most important birthday present of
The
her
most
life.
important birthday present of your entire life. Let's talk about displacement. Okay, so we sort of talked about this example before. We saw that how the area under the velocity curve could tell us about the distance traveled. The net area tells us about displacement, while the total area between the function and its horizontal tells us about the total distance traveled. So just so you know, the difference between displacement and total distance traveled, we can explain that.
It's a vector quantity.
Velocity is a vector quantity, yes, but I'm talking about displacement versus distance traveled. Yeah.
Distance is like the total you traveled, regardless of what direction you take. Displacement is the shortest distance from A to B.
Yeah, or you can just think of it as just relative to your original position, how far you moved away. What?
Because math.
It's math.
Right?
Right? So if I'm standing here, I walk 10 meters that way, and then I turn around 180 degrees, I walk 11 meters this way. My displacement is 1 in the negative direction, but my total distance travel will be 21, right? That's the difference. And how we compute it? Well, I can think of the displacement as just the definite integral. That's what it gave us. But the total distance traveled, I'd have to make sure my function is always positive. So when I'm traveling from there back to here, that technically would be a negative area in our calculation, so we have to make that positive. So basically what this means is displacement. Let's say S of t, position, v of t, velocity. The displacement for some time window from A to B is given by just the definite integral from A to B of the velocity. The total distance traveled, and this is just new distance moved relative to initial. Total distance traveled. On this interval is given by, it's almost the same. The difference is we want to get rid of those negative distances, right? So you just put absolute value, and that's the only difference. So whenever you travel, get a negative area, you make it positive. And that will tell you the total distance you traveled. And that's basically it. Let's do an example. See that first. Probably should have done displacement first. I'm going to write displacement first. A. Total distance traveled is given by what? It's just going to be the integral from A to B, 0 to 3, of the absolute value of the velocity function. So how do I deal with that, the absolute value of the function?
Piecewise function.
Is that supposed to be? I think I meant to write 5. I hope I meant to write 5. Okay, so how do we do it? Absolute value. What do we need to figure out?
The time.
No, there's an absolute value here. You need to figure out where it's positive and where it's negative. How do I figure out where this is positive and negative? Set equal to 0. And try to find the times, right? What are the times here? Try to factor. 5 and 1 must be minus and minus, right? So we know t equals 1 or t equals 5. So of course time starts at 0, and we have 1 and 5 to worry about. So where is it positive? Well, I know it'll be positive over here, and positive over here, and negative in here, because this is a parabola, it looks like that, right? So it means that on 0 to 1 I'm positive, but on 1 to 5 I'm negative. So I have to break my integral up into 2 parts.
But
Yes.
are we only doing that because it's absolute value though?
Yes, only because it's absolute value. Right? So it means like, technically here you would have negative distance traveled because it's distance going backwards. So you don't want that, so what we have to do is we have to take this part out and make that negative. So from 0 to 1, it's okay to keep the original function. But from 1 up to 5, 1 up to 3, because I don't care about up to 3, I would take the negative of the original. And so that would be the displacement. So take the antiderivative, 3 squared t plus minus 3 plus 3t squared minus 5t 1. So this would give us 1/3 minus 3 plus 5 minus 0 plus minus 3 cubed over 3 plus 3 times 3 squared minus 5 times 3 minus right, and then we just compute this. Does anything simplify or cancel? Not really. It's 1/3 minus 3 plus 5. Minus, this is just 3 squared, minus 9 plus 27 minus 15 plus 1/3 minus 3 plus 5. And what's this? Yes?
How do you know the difference between its absolute value or the line that you wrote like from history?
Well, you mean this line that I wrote from yesterday? This you only write after you did an integration.
Right.
And then you want to plug in limits. This happened at the beginning of the problem. This is absolute value. So we have 1/3 plus 1/3, that's 2/3. And what do we have here? We have minus 9. Let's take all the negatives. What do we have? Minus 3, minus 9, minus 12, minus 15. That's what? That's minus 27. So with the plus 27, those guys all die, right? Now what else do we have? We have 5 plus 5, that's 10. 5 plus 5 is 10, minus 3 is 7. Right? Is that it? So it's 21 over 3 plus 3. Or as far as the arithmetic. Is that right? Yeah.
Why isn't there plus c?
Oh, when you're doing definite integrals, there is no plus c because they would always cancel each other. Right? If I had a plus c, I would have a plus c here minus a plus c there. Right?
But like, if you were going straight there, like if it was just d equals the integral from 0 to 3, and you didn't have to split it up from 0 to 1 and then 1 to 3, like it would just go straight from 0 to 3. There would be only 1 plus c then.
Yeah, it will always cancel out with a definite integral. Always. Right, they never write plus c when you have a definite integral. You could write it, but it will always cancel itself. Okay, so B, right? Because you always have something plus c minus something plus c. You'd always have the minus c minus c. Okay, so now if we want to find the displacement, then we don't have to split anything up. We just take the definite integral. This was t squared minus 6t plus 5 t. Minus 0. So this is just 9 minus 27 plus 15. So what's the displacement? So that just means you actually moved 3 units backwards, right? So it means that this guy, he actually changed direction. He moved forward a little bit, then he moved backwards even more than he had moved forwards initially. C. For t from 0 to 5, when is the particle moving forwards? we're going to compute that to do the first part. So it's moving forwards for t goes from 0 to 1. It's moving backwards for t goes from 1 to 5. What's the other question? When does the minimum or the maximum velocity occur? What do we need to find?
One question. Which one do we use?
The last one. So we asked when is it moving forward, when is it moving backwards? We found those times. When does the min or max velocity occur? What do we want to find here? Huh?
Absolute maximum.
Absolute maximum. On 0, 5. Remember how we do that? So you have v of t is equal to t squared minus 6t. So first you have to find the derivative. T minus 6. This means t equals 3 is the only critical point. So then we need to find v of 0, v of 5, and v of 3. V of 0 is 5. V of 5 will be 5 squared minus 6 times 5 plus 5. Right? Which is 0. V of 3 will be 3 squared minus 6 times 3 plus 5. 9 minus 18 plus 5. 9 plus 5 is 14, that's what? Minus 4, right? So, max velocity is 5 on this envelope, and min velocity is minus 4. Slide into it. You forgot everything from test 3 already. So problems like this are pretty likely. We get 60% chance something like this will come on the final. Something that will definitely be on the final, area. This is the second application, which again, this is one that we've been talking about for a while. Area under. And it's a nice kind of area, so it's always the one where the function is positive and between the x-axis. I mean, you go over areas again in calculus 2 in far more generality, and I got carried away when I was writing down my notes. I was teaching it like it was top 2, and I hope top 1. I had to do like the watered down version. So this is just if f is positive on AB, then the area under F on AB is dx. The area under F, they can also phrase it as the area bounded by F and the x-axis. Right, so something like that. You'll see either one of these phrases, right? Area under the curve or the area between the curve and the x-axis. Do I want to tell you about the general?
No, you do. If it's not
I guess start.
If it's not the test.
Oh, okay.
Wait, if it's not the test, if it's not the test.
Okay. It's just top function math. Never mind.
Is it on
Okay. Example. It's very tempting though.
Don't do it.
That is a possible question. And it would sort of look like that. They'll give you this sentence. Find the area under this curve, or the curve bounded between this and y equals 0, which is the x-axis. And they'll give you a limit for the x's. So from x goes from 0 to pi. And here, the area is just going to be the antiderivative from 0 to pi of the sine. Okay, so how do we do that? Antiderivative of sine is what? Minus cosine between 0 and pi. Is that plug in minus cosine pi minus cosine 0. Cosine of pi is?
0, 81.
No, minus 1. Minus minus 1 gives you plus 1. Minus cosine of 0? Huh?
Cosine of
Cosine of 0 is 1, so this is minus 1. Right? So there's 2. Are you guys doing that on purpose or?
I'm not going to choke on it.
I have video evidence that my professor abused me in class.
Oh my god. No. Don't go to wall shot, please.
That part of the tape would be conveniently damaged. On YouTube, they were like 5 seconds. For like 5 random seconds. Sorry, someone divided by 0. It happens sometimes. Okay. Area under x between you more than likely see something like this, or just want to give you a variation of phrasing. There are tons of ways they can say something. So like I say, top one is the easy case. You don't really have to think about it much. You just take that function, you integrate it over here. This is not super interesting part. In calculus 2, they make this a little bit more interesting. Just a little bit.
Define interesting.
You really don't want to know.
They give you 2 functions. So like I said, you know, there's this curve like this. And then they find the area between the 2 curves. You know? Things like that. That's nice.
Didn't I say this? I know.
The concept is not that complicated. How do we integrate this one? Distribute the x, right? You remember, you don't know the product rule for integrals yet. It's a very weird rule. So
There's actually a rule?
you have to actually distribute. Yes, it's called integration by parts. It's sort of how you would integrate things to reverse the product rule. But for now, we don't know it, so we have to multiply out. Wouldn't do it here anyway. And now we just apply the power rule to each term. So this is just x to the 4th over 4 minus 2x squared between minus 2 and 0. So it's 0 minus open bracket, very important. Now we have minus 2 to the 4th over 4 minus 2 times minus 2 squared. So I just 2 to the 4th, 16 divided by 4 is 4. Minus 8, so this is just 4. Oh, but by the way, area should be positive.
Always?
Yes.
Or not?
Always.
They have negative area. You have to go to the reverse of it.
Under the x-axis, yes, negative.
What if the curve is below that?
Then you would make it. Then you make it positive.
We still not this.
Yeah, because you're looking at area,
Alright. Oh yeah. I got
not
you.
net area. We actually want area in the
Oh, yeah.
sense that where you.
So what about if you have multiple?
You won't be given multiple.
Alright.
It's calc 1. Okay. Okay. So this one area. What's the area? How would we find it? Integral of 0 to pi over 4, 3 cosine x dx. What's the integral of cosine? Positive sine. 0 to pi over 4. So this is just 3 sine pi over 4 minus 3 sine 0. Sine of pi over 4. Right, go 2 over 2. Sine of 0 is 0. Third application. Average value. If I have a function, I want to find out what is the average output of this function on some interval. I can actually use definite integrals to tell me this. How do you find the average of n terms? Well, right? This is how you do the average. There are finite terms, right? You add up all the terms, you divide by the number of terms. So, if you want an average of all terms, meaning you're on a real valued function, so it takes on an infinite number of values. All you do is take the limit as n goes to infinity of this function. That's just the sum of xi over n. I go from 1 to infinity. Now we know from our study of Riemann sums that delta x is actually b minus a over n, right?
Yeah.
This means I can actually rewrite n in what form? It's just b minus a over delta x, right? You take b minus delta x equals b minus a over n, solve for n, you get that. Subtraction you can flip and multiply. This means you just have the limit as n goes to infinity of 1 over b minus a times the summation of f of xi times delta x. But we know that this guy actually gives us the integral from a to b, and so we end up finally with the formula. Yeah.
So when you put xi, you mean a plus I delta x? When you put xi?
Yeah, but we don't need to go to that specificity in this case.
Alright.
I'm just counting all these x values. So this means the average value, the notation is f little a b e is given by 1 over b minus a, the integral from a to b f x dx. So this is the average value that your function gives on the interval a t. Huh?
So you just divide it by the difference.
1 over the length of the interval times the integral. Yeah.
Is that an F or an integral with a line in it?
This?
No, left. Left.
That's it.
Oh, it's an f. It's an f.
Oh.
It's f sub a b e. That's the notation for f average.
Oh.
A b g. We also have the value theorem for integrals. It uses the old mean value theorem, but I'm just going to write down the formula here. If f is continuous on a b, then there exists C in AB such that f of C is equal to the average value. Now let's do an example of that. By the way, if you're keeping track, this is pretty likely to come on final. 8 out of 10 or 9 out of 10 chance. This one is far less likely, but it's important anyway. And it might come on. Small chance. Example. So I know x squared gives me a bunch of outputs on this interval. What is the average output? How does this function perform on average is what we're trying to figure out. And the definite integral is the way we can do it. We're thinking of this as part A and part B, referring to the same function. And yeah, average value is just a formula. So you memorize the formula and you just apply it. Here, f average is going to be equal to 1 over b minus a. Remember, a, b is the notation for the interval given, so it's just 1 over 2 minus 0 times the integral from 0 to 2 of this guy. So that's just 1/2 the integral from 0 to 2 of x squared, x cubed over 3 between 0 and 2. This is 1/2 times 2 cubed over 3 minus 0. So this is just 4 over 3. So the average output of x squared on that interval is 1 1/3. So if you could possibly add up all the x squares between 0 and 1, divide them by the number of numbers there are, that would be what you would get. Right? But you see, the integration makes it a whole lot easier, right? You don't have to add up numbers. So you can see This has a lot of applications. A lot of times we want to know how something performs on average, but there's just too many data points, right? You don't want to waste your computer's time plugging it into Excel and saying, okay, add up these 2 million values and find the average.
Wait, what
No,
does
you
this
can
do
just do it.
again? What does this do again? Find the average on
The average value, right? It's just like if you have, if you have 5 numbers, you want to find the average.
Yeah.
You add up the numbers divided by 5, right? What if you have 2 million numbers? You don't want to take the time to add up 2 million numbers. You can just find a function that gives you the numbers, and then do this integral, and it would be, if it's a continuous function, that would be the exact number. If it's just discrete values, this at least gives you an approximation. The more values you have, the more values.
And this is the watered down version, up to?
No, this is that. Yeah. The area we're not very serious with. This one says such a C exists. Mean value theorem for integrals since f of x is continuous. How do we know f of x is continuous? It's a polynomial. Right, so now this means there is a C such that f of c equals c squared, right? I just put c into the f function, equals the average value that I found here, which is 4/3. This means that your c would be plus or minus 2 over radical 3. So take c equals 2 over radical 3, right? You ignore the negatives because I want one in this interval. So on the last test with the mean value theorem, that was the 2 mistakes that people made. One, they forgot to plug into the derivative so that they could solve their equation. The other one is they gave me both the values. You have to see which value is in the interval of interest, right? The minus 2 over radical 3 is not in between 0 and 2, so I ignore it. That's it for applications.
So I didn't get an answer.
Huh?
I didn't get an answer.
You didn't get what?
Twist.
That's because you came in late. Where's Ashley? What? Keyboard?
She got sick.
Okay, 4.5 substitution. Woo!
Last lesson.
This is the first integration technique you're going to learn when you go to Calc 2. They're going to expect you to know this already. And the first couple of days it might confuse you, but after that it's going to be the easiest thing, and you're going to wish all your integrals were integration by substitution, but unfortunately you realize they aren't. So, how do you know when to use it? Use to integrate composite functions. Right? That's functions inside of functions. Basically, they developed it by it's the reverse of the chain rule. Right? Later on, you're going to learn the reverse of the product rule and all that, but this one in particular is the reverse of the chain rule. Right, the reverse of the product rule is integration by parts, which is in Calc 2. The rule is the following. Of course, there's some example. If G is differentiable, and F is continuous, the integral of f of g of x times g prime dx is just equal to f of g of x. Usually we say u equals g of x, and so just that's not what I wanted to write. I want to write you get another integral. I'm going to explain what this formula means. Except for perhaps a constant factor. Note the derivative of u must be a factor the integer. All right, so the idea is we're going to do a substitution. We're going to do it for g of x, but in order for this to work, the derivative has to be multiplying the function. Right? If this g prime isn't there, substitution won't work. Right? So it's not something that always works. So once you think, oh, I'm going to do this substitution, you have to make sure you can find the derivative somewhere else. That's important. We choose u to make the integral look like one of our basic rules. So remember we have the power rule, and we know the integral of sine and cosine and nice functions like that, but the functions aren't always nice. So what if you get things that look kind of ugly? How do we transform them into something nice? Well, in this situation, we can. For example, x sine squared. Or integral of did everyone copy this down?
No.
Okay, so remember we know the basis rules, right? We know how to integrate something that looks like x to the n. We also know how to integrate something that looks like sine x. This does not look like sine x. It's actually x times sine x. So now we can't really separate the integrals. Integrals do not distribute across products. So what we do is we try to transform it to look like sine x by using substitution. Notice that there's a composite function present. I have sine, and there's x squared plugged in, not just x. So I know I can integrate something that looks like sine x, so why not make this look like sine x? Which means I would say let u equals that x squared. Right? And so now I would get rid of the square in here because I don't know how to integrate things with sine squared, where the angle is squared. And so what you do at this point is you're going to take the derivative. Right? This is why the derivative is important that it's there. So if you take du dx, you get 2x, right? Which means du is equal to 2x dx. Right? Mostly we will skip this step, but I just want to show you that you just write this down. Right? So you have u equals x squared, du would be 2x dx. So now you see here, what you're going to want to do is you're going to want to try to swap things out of this integral so that I get something nicer. So we already know we can replace the x squared with u, but then there's this x dx here. Right? Now I know how to transform 2x dx. How do I figure out how to transform x dx? Right, solve for x dx. So this means that 1/2 du would equal to x dx. And now what you do is you go and swap things out. So it turns out that this integral would be equal to 1/2 du is going to replace my x dx. And then sine of x squared is now just sine of u. Right? So this thing just becomes, it's 1/2 times the sine of u du. And this looks like a basic rule, right? It's just like sine x dx. Remember I told you about dummy variables. It doesn't matter if it's an x or anything else. You can just apply the old rule. So the integral of sine is minus cosine. So this gives us minus 1/2 cosine u plus c. And now we have to replace u with what its original value was. So it's just cosine of x squared plus c. And you can check that if you differentiate this, you will actually get that. So to go over u-substitution, or substitution, is just you replace some function with u to transform it into a nicer function. Whatever function you choose, its derivative must be a product somewhere else in the function. Right? And then, when I said except for a constant factor, the reason why we don't care about constant factors is because we can always just divide them out. Right? So you don't even care if it's off by a constant. And that's that. Do a couple more examples. So this one is a product. We can't do that one. But we also wouldn't like to multiply out. That's 20 power. I'm not going to waste my time multiplying that out, getting 21 terms and doing the power root 21 times. Right? What I could do though is realize that the thing that's making this thing complicated is this guy to the 20th power. If it was just x to the 20th power, it would be nice. So I'm like, wouldn't it be nice if that was a single variable? How about we make it a single variable? U equals this. Now remember, whatever I choose, I have to make sure its derivative is somewhere else in the function. The derivative of x to the 4th is going to be 4x cubed, and I see there's an x cubed here. It doesn't matter if the constant is off, I can always divide them out. So I say u equals 5x to the 4th plus 7.
You take the derivative?
Then you take the derivative, because you have to figure out that du. You have to swap out the dx as well. So this would give you 20x cubed dx. Right? So now you know that 1 over 20 du is equal to your x cubed dx. And so you can swap out this integral. You have this 3 here, now over 20. Because I'm just plugging this into there. The x cubed dx is replaced by that. And so now I have this guy to the 20, but that guy is just u. So now I just have u to the 20. Should I write it down? So I have 3 times, I put 1 over 20 du. The d's always go to the back, times u to the 20. guy here becomes this guy here. And then the 5x to the fourth just becomes u. So now I can actually rewrite this guy, 3 over 20 times the integral of u to the 20 du. And now that looks like a power rule, right? So it was really complicated before, did a substitution, now it's really easy. So now, what do? We add 1 to the power, divide by the new power. This is just 3 over 20 times u to the 21 over 21 plus c. So this is just 3 over 20 times 21 times, now you replace the u with this guy, it's 5x to the 4 plus 7 to the 20 plus c.
Wait, so you find all that, then you do the antiderivative of that?
Yeah, do the antiderivative here.
Alright.
Right? You did all this just to rewrite your integral in a nicer form.
Yeah.
Now you have a rule for this. You didn't have a rule for something like that, but you have a rule for something like this. Right? This is another thing that we don't have a rule for. We don't have a rule for anything that has a radical in it or a product of functions. What is a good substitution here? U equals x cubed plus 1. Why would x squared be a bad substitution? Why would u equals x squared be a bad substitution?
Because that derivative is not in the way.
The derivative would just be x. There's no x multiplying the thing anywhere, right? And it wouldn't simplify this thing. So it doesn't simplify, the derivative is in somewhere else. However, if I say u equals x cubed plus 1, then the derivative is 3x squared dx, and I have that x squared dx. So this means that 1/3 du is equal to x squared dx. And so I can swap out my stuff. This is 2 times 1/3 du replaces the x squared dx. And now I just have a radical u. So this is just 2/3 times the integral of u to the 1/2 du. And again, I can use the power rule for that. So I went from something really complicated to something that was really nice. I can apply my rules to it. So this is just 2/3 times 2/3 u to the 2/2 plus c, which gives us 4 over 9 x cubed plus 1 to the 3x plus c.
Oh, good. Yeah. That was good. I like that.
You guys want some more example?
Yeah, we want some. Because then we can test.
I mean, we're in overtime. If you have to leave, just leave quietly. Just watch the video on YouTube.
You're still gonna go on?
Yes.
You guys are saying?
This is for our GPs.
No, that's why it's hot.
Leave quietly.
It's not fair. Half the time is mine.
I want you guys to try this one. So evidently from the test, a lot of people think the integral of sine squared is sine cubed over 3. It's not true.
I did that
Because you add 1 to the power and divide by the power in the power rule, you can only do that with polynomials. You cannot do that with trig functions. Okay? Remember, be very specific with the rules.
That was a trig identity, right?
Yeah, you could have, in the test it was a trig identity. Cosine squared minus sine squared was cosine 2x.
Could you have done this if you knew how to do it? Like this stuff?
Come again?
U-substitution. Would you have given credit to someone who...
If you did it correctly, I would have given you credit, yeah. Some people attempted it. Some people attempted to do it, so. Okay, what do you think a good U is for this one? U equals 4 minus x. So du would be? Minus 1 dx. Right? So this minus du would replace dx. So I just put a negative sign here, du. And this guy here will replace dx. Now this guy here is just u now. So it's 1 over radical u. So it's just minus the integral of u to the minus 1/2 du. This is u to the 1/2 times 2 plus c, or minus 2 4 minus x to the 1/2 plus c.
Wait, how do you find the regular derivative of u minus 1/2 if you add?
Add 1 to the power, divide by the new power.
Alright.
Right, so it's minus 1/2 plus 1 gives me positive 1/2. If I divide by 1/2, it's multiplying by 2.
Wait, that's an antiderivative or derivative?
Antiderivative.
Oh yeah, antiderivative. Yeah.
We only do the derivative here to solve for the dx.
Yeah.
But then after that, the goal was originally to do an antiderivative. Take an integral. What's u here? U equals 3 plus x squared. Why would I not take the cube root? Because when you find the derivative, I won't have the derivative there. Right? However, if I find the derivative of this guy, that's just 2x dx. And this x dx is right there. Right? This means 1/2 du gives me that x dx. So I can rewrite this integral as 1/2 du times 1 over the cube root of u. Well, that's 1/2 times u to the 1/3 du minus 1/3 because it's on the bottom. So you add 1 to the power, that gives you 2/3 divided by the new power. 0/2 plus c. So this gives you 3 over 4 u plus 3 plus x squared plus c.
So when we do definite integrals with the numbers with a sigma, with that.
Yeah, so if they give you numbers, you can do this and then plug in the numbers here.
And then you
There's a way you can change the limits, but I don't want to show you that now. Maybe Monday we can talk about it. Tuesday we can talk about that a little bit when we're going over the homework and stuff. What about here? U equals cosine. Because the derivative is minus sine, right? Right? If I knew use sine, the derivative would just be cosine. I'd have a whole bunch of cosine. Yeah.
What you say in the answer is there's supposed to be 2 over 3, but then there's something.
Coming in?
The power
2 over 3.
Yeah, the 2 over the power exponentially.
Oh, right here, yeah. I missed it. So the 2 over 3 we forgot. So this means minus du would replace our sine x dx. So what is our integral now? Minus u to the third du. This is u to the fourth over 4 plus c minus cosine to the fourth. Who is u here? For this one?
How is it cosine? Because you put the u to the.
Right, cosine cubed is just, this is just cosine x
Oh, I get it.
cubed, right? And then there's a sine x attached to the bottom.
No, again, like du is the sign.
Yeah, the du replaces that sine x.
Oh, yes,
What's a good u for this one?
Let's choose 1 plus 1.
U equals 1 plus radical x. So your du would be equal to what?
1 over 2.
1 over 2 radical x dx. Which means 2 du gives me that 1 over radical x dx, which I see right here. 1 over radical x as a factor. So then the integral now becomes 2 du replaces that 1 over x, and this is just 1 over u squared. This is just 2 times the integral of e to the minus 2 du. So you add 1 to the power, divide by the u power. And this gives us minus 2, 1 plus radical x, minus 1 plus. Well, there's Are you guys actually seeing how to swap things out?
Yeah, I kind of get it better.
Not really, or not really.
Give me like 2 days now.
Yeah, it was the same for me when I learned it first. I was like, yeah, I get the concept, but it's sort of shady. But after a couple of days of working through it,
Nah,
it's
it's
like,
pretty simple after you get it. Like,
yeah,
Yeah.
yeah.
You got 100 and everything?
No.
I feel like you did.
How do we do this one?
X squared. No, actually, no.
Equals x? X squared?
This is sine.
If I let u equal sine x, what would happen? The du would be cosine. Is there a cosine here?
No.
Can't use that.
Using trigonometry?
Trig identity. Which one?
Oh, 1 plus. Is it 1 minus
Hey. I'm a formula. This is just 1/2 of 1 minus cosine of 2x.
The one I don't.
Wait, do you have to use this?
Now it's funny, but that's the sort of thing that sometimes how you have to think about. You're like thinking, okay, how do I do this? Substitution, right? You just throw an idea out there, and then you follow the logical conclusion of your idea. You're like, well, if I did substitution, what would I substitute? Well, there's only the sine. Oh, I need a cosine. So then you're like, okay, substitution won't work. What else is there? It's a trig function, a trig identity, right? And then you start to think about it. Do I know a trig identity that can get rid of that square? It turns out the half-handle formula is such an identity. So what you would do here is you can actually split, well, you can split this guy in two. That will probably be easier. In general, you don't have to do this, but I think it'll be easier to digest if I do that. Now this one we know how to integrate, right? That's just x. How do we integrate this one? Cosine 2x.
Oh, u equals 2x?
U equals 2x, right? So it's not just cosine of x anymore. It's cosine of 2x. There's a composite function. So what I would do for this one is u equals 2x. So my du would be 2 dx. And so 1/2 du would equal to dx. So over here, this is just, well, let me just keep that, 1/2 x minus 1/2 times, now we're just doing the substitutions. 1/2 times integral of cosine g. So this is just 1/2 x minus 1/4 times integral of cosine u. Integral of cosine is sine minus 4 sine 2x. See. And a similar technique would be used to integrate cosine squared. You'd use the half angle formula, but this guy would be a plus.
Gotta memorize all those two
By the way, in general, eventually you should get to the point where you wouldn't have to do u-sub or something like this, right? You should understand whenever the derivative is going to be a constant, you just divide by the constant, right? Just going to divide by the 2. Right? So, for example, if I ask you, what is the antiderivative of sine 5x dx? Figure out, this would be your u, so you just cancel by putting that 1/5, right? Just 1 divided by the constant, right? So it's minus cosine 5x. Now it's important that if the derivative is not a constant, you can't do this. It won't work. But whenever it's a constant, you don't really have to think about it. You just divide by the constant. What's the antiderivative of cosine pi x?
1/5
Sine of pi x.
Should put down the test actually.
Yeah, so on the test, that's what I was going to get to. On the test, we had the integral of something like sine, I think I put pi x over 3 or something like that. Where you can realize this was just sine of, this is just pi over 3, which is a constant times x. The derivative of that would have just been pi over 3, so you just multiply 3 over pi. Times the minus cosine. But that's sort of, go home, you mull this all over, you should, by the end of the weekend, you should be good. The homework chapter 4 we do on Tuesday, we'll go over problems and questions you might have on the test. So we'll stop here.